I want to now introduce you to another type of a coupled analysis, and that's the coupled effect that results from the rapid drawdown of a reservoir, for example. In a rapid drawdown case, the reservoir has been sitting there for a long time and has established long-term steady-state conditions. Then the reservoir is going to be drawn down over a period of 5 days. And we know that as the reservoir disappears, of course, the excess pore pressure in the embankment disappears with time. I'm going to concentrate in this workshop session here on the sigma coupled analysis, although in this file there are other analyses for the seep-only case and for the instantaneous rapid drawdown case. I'm going to concentrate only on the coupled analysis with the drawing the reservoir down over a period of 5 days. There are some special boundary conditions that we need to consider in this case. The first one is to recognize that when we remove the water weight, when we remove the reservoir, we are removing the water weight. As a result, we get a change in total stress. We get a total stress change. The way we do that in sigma W is to define a special type of boundary condition, which is known as a hydrostatic boundary condition. And the hydrostatic boundary condition is a function. And since we are drawing the water down, the elevation of the water current is less than the elevation in the past. As a result, the delta H becomes a negative value. And the negative value, in essence, means there is uplift. So the removal of the water will apply forces on the surface to simulate the removal of the weight. Now, these forces are being computed automatically by knowing that there is a delta H in the water level, and this delta value is negative. As a result, we get uplift forces on the embankment. Now, in real life, there are no uplift forces, but numerically, to simulate unloading, we have to apply forces on the finite elements to simulate the effect of a load removal. We also need a special hydraulic boundary condition. Recall that we are doing a coupled analysis, so we have to say something about the sigma boundary conditions or the stress-strain boundary conditions, but we also have to define the hydraulic boundary condition, and we have to define the pore pressure changes, which we will do through a function as the reservoir is being drawn down. But above the reservoir level, there could still be a seepage face here, and so we have to make sure that we tell sigma W to check for the possibility of a seepage face. Going then to GeoStudio and opening up SIG 18. This is the analysis tree in this file, and we will start with an initial steady state condition which establishes the pore pressure under long-term steady state conditions. And then in the file we have a seep alone analysis and then a seep instantaneous analysis, but we want to concentrate here on the coupled sigma analysis to simulate the rapid drawdown. To begin with then, what we need to do is establish the long-term steady-state case, and in this particular case our analysis is a SEEP analysis. It's a SEEP analysis and it's a steady state analysis, and you are all familiar with how to do this by now, and so we can briefly look at the results. And here is the long-term steady state condition to establish the initial pore water pressures. Then going back to the defined view under the analysis tree, the next thing we need to do is establish the state of stress in the ground when we are under full reservoir level. Once again, notice that we are doing an in situ type of analysis. We are going to get the pore water pressures from the parent, and the parent is the initial steady state seepage analysis. We are doing an in situ analysis. There's one important point about this particular case that we have not encountered before, and that is in the in situ analysis we have to account for the weight of the reservoir water with a boundary condition. So you can see that we have a boundary condition here, the dark blue arrows. This boundary condition, key in boundary conditions, the boundary condition has been created here and is reservoir pressure. What is significant about this boundary condition is that it is a type under the category of stress. There is a special type of boundary condition called hydrostatic pressure. The elevation, or the action in this case, is 19 meters. This is the full supply level of the reservoir, and the unit weight of the material I have rounded off to 10 kilonewtons per meter cube, representing the unit weight of the water. We have selected hydrostatic pressure from our list of stress type boundary conditions. So in this case we have turned on gravity, we have the self weight of the material, plus we get our pore pressures from the long-term steady state seepage analysis, but it is incredibly important to also apply the weight of the reservoir water, and this has to be done through a boundary condition. It is rather unfortunate, but it is easy to miss this particular step in establishing the initial steady state and initial stress state conditions. So we won't take any time to dwell on it, but here are our initial stress conditions, and we have included the weight of the water. So now we know what the state of stress is in the embankment and in the foundation before taking away the reservoir. Under our analysis tree, the first step then is to do a coupled drawdown with time analysis. Notice that we are again doing a coupled analysis. We are going to get our initial stresses from the parent, and we're going to get the initial pore water pressures from the parent. When we did the in situ analysis, we got the pore pressures from the steady state seepage analysis. Those pore pressures are now part of the in situ analysis, so now we can get the initial pore water pressures from the parent. But the important thing here is that we are doing a coupled analysis. Our boundary conditions then, taking a look at the boundary conditions as the reservoir is being taken away, key in boundary conditions. We are removing the reservoir with time. And so once again we have a hydrostatic pressure type of boundary condition, and we are going to get the appropriate pressure from a function. And the function is this function here, where we have the full supply level at time 0, and in 5 days we have drawn the reservoir down to elevation 10. So we are drawing the elevation down over time. So that is a stress-strain boundary condition, and as I've already noticed, the change in the elevation of the reservoir results in a force that represents the removal of the weight of the reservoir. We must also define the hydraulic boundary conditions. Once again, notice here that we are selecting a function, and we have a reservoir level with time function, and we have checked the fact that there could still be a seepage phase above the reservoir level. So here is the drawdown function again. The full supply level, drawing the total head. It's the total head that we are drawing down over a period of 5 days. So we have specified 2 types of boundary conditions on the ground surface which was in contact with the reservoir, and the reservoir is going to disappear with time. We can click on Solve if the problem does not contain the solution. In my case here, I already have the solution, and we can now begin to take a look at the results. I'm going to turn off my contours, and going now to time 0. This was the starting case, and now we are drawing the reservoir down. This is after 1/2 day. Drawing the reservoir down after a day and a half. After 2.5 days, and after 4 days, and after 6 days, the reservoir has been completely drawn down, but the pore pressure inside the embankment continues to dissipate as with time. And I believe that we have a maximum of 30 days after the reservoir was started to be drawn down. Going to the results view and looking at some of the highlights of the results under Draw Graph, what's rather interesting is that if we look at the deformation at a particular point, we are looking at the vertical deformation at the toe of the embankment here. So we are plotting y displacement versus time, and it's interesting that the soil or the embankment and the ground is rebounding. It's lifting up as we remove the weight of the reservoir. So here's at the end of 1, 2, 3, 4, 5 days. At the end of 5 days, the soil is rebounding due to the removal of the weight of the water. Then as the excess pore pressure dissipates, the soil begins to settle back down. So it comes up and then moves back down. This movement of the ground due to a total stress change has an effect on the pore water pressure response, which we will see in a little bit. Clicking on the pore water pressure, we are looking at the pore water pressure at this particular point right here. We have a plus sign. And we notice, of course, the pore pressure head. We're talking in pressure head that as the reservoir comes off, then of course the pore pressure is dissipating, and then after day 5, when all the reservoir is gone, the pore pressure continues to dissipate as the excess pore pressure drains out of the embankment. Now, obviously, the major point of interest in here is what is happening with the stability of the embankment during the rapid drawdown. We can now go to a slope stability analysis, and notice that we are doing a slope W analysis. We're going to use a Spencer type of analysis, but we are going to get our pore water pressures from our parent, and our parent is the coupled drawdown analysis. And under time, we have selected all. By selecting all, we get the change in factor of safety with time. Going to the results view then, here is the factor of safety at the end of 30 days. Here's the factor of safety immediately after the start of the rapid drawdown. And as the reservoir is being drawn down, of course, the stabilizing effect of the weight of the water is disappearing, and as a result, the factor of safety is going down. But then, at some point after the reservoir is gone and the pore pressure continues to dissipate, then the factor of safety increases. We can look at this in summary view by going to Draw Slip Surfaces and clicking on factor of safety versus time. And so here we see a graph of the factor of safety during the reservoir drawdown. Under long-term steady-state conditions, the stability of the upstream safe face is very high, but then as the reservoir disappears, the factor of safety is going down. But then we reach a point where the factor of safety is a minimum, and then once again, as the excess pore pressure dissipates, the factor of safety begins to increase. So it is obviously, from a design point of view, it's this lowest factor of safety that is of interest to us. So that shows how we can use the time-dependent results in a stability analysis to get something like a factor of safety versus time. I will allow you to investigate these other analyses that I've already mentioned, and that is a SEEP alone analysis and then an instantaneous drawdown analysis. These analyses are in the file, and you can look at the results at your interest level and at your pleasure. Going back to our PowerPoint presentation then, in summary, here is a comparison of the SEEP alone and the sigma W coupled pore water pressure response due to the reservoir drawdown. And you can see here that the pore water pressure is somewhat lower for the coupled analysis. Doing a SEEP alone, we have a slightly higher pore water pressure at the same time. The reason for this is that removing the weight of the water and doing a coupled analysis, there is a tendency for a slight amount of rebound of the soil, and this tendency for rebound has an effect on the pore pressure response, and as a result there is a slightly lower pore pressure at the same time than what we would get from a SEEP alone analysis. SEEP alone does not consider a change in total stress. Now, in a coupled analysis, we are looking at a change in total stress as well as a change in pore pressure. However, in the long term, you can see that the pore pressures are identical. Here are the factors of safety versus time. Obviously, SEEP alone gives you slightly higher pore water pressures. As a result, you get slightly lower factors of safety as the minimum values. The sigma coupled value gives a somewhat higher factor of safety. Very briefly, the instantaneous drawdown. While we can do an instantaneous drawdown, the results are rather unrealistic. This cannot happen in the field. It is impossible to remove the reservoir with instantaneously, although this assumption is often made. But the results between drawing the reservoir down very fast over 5 days and taking the reservoir away supposedly instantaneously, the results are quite different. If we were to do an instantaneous analysis, the factor of safety would be well below 1. Taking all the reservoir away suddenly, completely, would say that we have a factor of safety that is way below 1 and that we should get a drawdown failure. However, taking the drawdown over a very relatively rapid period of 5 days, the minimum factor of safety is even greater than 1.3, which would indicate likely a safe design in a safe situation. So, doing an instantaneous drawdown is rather an unrealistic thing to do, an unrealistic condition under field situations. And so now you have a tool. You can either use SEEP-W alone and draw the reservoir down over some realistic period of time, or even do a sigma-W coupled analysis and draw the reservoir down with time, and you will get much, much more realistic results. That brings us to the end of this brief introduction into another type of a sigma-W coupled analysis. In this case, the change comes from the removal of the weight of the reservoir water and the corresponding changes in hydraulic boundary conditions that occur as the reservoir is being taken away.